Hello. In the previous lesson, we looked at our two basic impedance circuit transformations. We talked about how to transform impedances connected in series into their equivalent impedance, and how to transform impedances connected in parallel into their equivalent impedances, and also, of course, how to transform combinations of series and parallel impedances into their equivalent impedance. In this lesson, we're going to add a third, slightly more complex impedance topology. We're going to talk about what's called the Delta-to-Wye transformation. You should have already seen it in Circuits 1. And like everything else we've done so far with phasors, basically we just treat everything as resistors. So it's super easy. There's just a handful, not even, just basically one simple formula that you need to have memorized. And other than that, it's just pretty simple arithmetic. So we'll go through, see what those formulas are, and then work out an example. So let's get into it. All right, so before we actually talk about what those formulas are, let's go ahead and try to draw out a delta and Y circuit. So let's see, we have a first node, call that A. And one impedance. To another node, call that node B. And down here, we'll have a third node, which we'll call C. And then we'll have an impedance connecting B to C. And then we'll have an impedance connecting A to C. And we'll label them according to the node that's on the opposite side. So this top one here that connects A and B, we'll call that one Z of C. And then the one that connects B and C, we'll call that Z sub A. And then, of course, the one that is connecting A and C, we'll call Z sub B. And this blue one is our delta topology. Now, what we'll do is we'll add, to transform it to Y, we'll add a node here in the center, and then we'll connect an impedance from B to that node, from A to that node, and from C to that node. The one that connects from A we'll call Z sub 1. The one that connects B is Z sub 2. And the one that connects to C is our Z sub 3. So this one that's given here in green is our Y topology. So we want to go back and forth between two of these. So we need two sets of transforms, two sets of equations. So we'll call this first one, the one that we've named this lecture after, the delta to Y. And those equations are Z1, they're pretty simple. Z1 is equal to the product of the other ones, right? The ones that sort of connected in here. So Z1 is ZB times ZC. Notice are the ones that connect to what is Z1. And that's going to be over then the sum of all the impedances. ZA plus ZB plus ZC. Z2 is just equal to, so we look at Z2, it's connected to ZC and ZA. So that's the product ZC times ZA over the sum of all of them. ZA plus ZB plus ZC. And then finally, Z3 is just, it's connected by A and B, so that's going to be ZA times ZB, and again, it's over the sum of all the impedances, ZA plus ZB plus ZC. So there we go. There are our three equations, three very simple equations for our delta to Y transformation. So now here on the flip side, let's flip it over. And if we want to go the opposite direction, we want to perform a Y to delta transformation. we also have some pretty simple equations, and it's sort of just in reverse. So the first one is if we want to find Z sub A, what we're going to do here on the top is sort of a chain of all of the products. Z1 times Z2 plus Z1, plus Z2 times Z3 plus Z3 times Z1. So back around to Z1. And then for A, it's going to be over Z sub 1. And then we will repeat this pattern for B and C. So ZB is just going to be this same structure, Z1 times Z2 plus Z2 times Z3 plus Z3 times Z1. All of that over for ZB, that's over Z2. 2. And finally, for Z sub C, same deal on the top, Z1 times Z2 plus Z2 times Z3 plus Z3 times Z1 over, you guessed it, Z3. And there we go. There are our equations for y to delta. And that's all we need to learn for this lesson. It's just what these formula are. So for converting from delta to y, here are our equations here. And from y to delta, here are our equations here. So now let's dig into an example of doing some circuit analysis with the delta to y transformation. All right, in this example, they've given us a relatively complex circuit, but they've done us the favor of sort of putting everything in phasors for us, so we can skip over that step. We've got a voltage source that's here at 12 volts at an angle of 0 degrees, and we've got a sort of soup of impedances down here. And what we want to do is just find the current I that's sort of flowing out of the voltage source. Now, if you're following along in the textbook, this example wants you to also find the current sort of flowing through each little section of this circuit. I don't care so much about that. I want to focus on really just doing the delta to Y transformation and seeing how we can calculate this current. Everything else to me just seems kind of like busy work. So let's jump in. What I want to do is, we can't necessarily get this 10 ohm resistor here that's kind of messing things up. So what I want to do is take the bottom half of this circuit and convert it to a Y topology, right? It's already in a delta, so I want to make it into a Y. So let's just consider that section right there. So we have what we'll consider our A node, which is connected to our B node through a 10 ohm resistor. Then from B down to C at a capacitor that is at minus J20. And then from A to C, we have a resistor through an inductor, and that's 20 ohms and J 60 ohms. So then, of course, we want to take this and convert it to something that looks like this. We have A, some impedance, scroll down a little bit, B on the other side, and then another impedance down to C. Because if we're able to do this, then in our main circuit, once we have our Y topology down on the bottom half, we'll be able to just use regular series and parallel impedances to get our equivalent impedance. So let's see, if this is our C sub C, that's our Z sub A. So let's actually write some of this stuff down. ZA, ZB. So we'll say that ZA is equal to just 10 ohms. ZB is equal to 20 plus, since these guys are connected in series, 20 plus J 60 ohms. And ZC is equal to minus J 20 ohms. And then over here, we're going to be finding Z1, Z2, and Z3. So let's just do it with the techniques that we saw in the previous part of this video. Remember, our equation for Z sub 1 is ZB times ZC over the sum ZA plus ZB plus ZC. All right, let's first actually figure out what is this sum, because we're going to use it over and over again. So ZA plus ZB plus ZC is equal to 10 plus 20 plus J 60 minus J 20. So that's going to be equal to 30 plus J 40. So we'll just kind of keep that and use it as we go down the chain here. So let's see, Z1 is equal to, ZB is 20 plus J 60 times ZC, which is minus J 20, and it's going to be over our 30 plus 40 J. Now we've got, let's see, Z1, we're going to factor in that top part, so we'll have minus 400 J. Ooh, I made a mistake, didn't I? Ah, yeah, we made a mistake here right off the top. That is incorrect, and that is incorrect. Those guys are flipped over. Our ZA is our, down here, the minus 20 minus J20, and our ZC is the 10 ohms. So I'll need to flip that over. Let me erase that section. I was wondering why I was getting something that didn't match my notes. So let me erase. Oh, come on. Give me the eraser. There we go. So that's just times 10 ohms. So we factor the 10 through, and we're going to get 200 plus J 600 ohms over 30 plus J 40. Remember, we're going to multiply by the complex conjugate, 30 minus J 40 over 30 minus J 40. Now, if we factor this out, I'm going to go ahead and skip over some of the arithmetic. I'll leave it up to you to FOIL these guys together, but that you'll end up with 30,000 plus J 10,000 over 2,500. Don't forget that the bottom part down here, the denominator, is just going to be 30 squared plus 40 squared. So when we solve that, we'll be left with 12 plus J4 ohms. So now let's do Z sub 2. Remember from previous section, Z sub 2 is equal to ZA times ZC times ZC over the sum ZA plus ZB plus ZC. Z2 is going to be, so ZA is our minus J20 times ZC, which is 10 over our 30 plus 40J, sum there. And I'll go ahead and leave the arithmetic because I'm going to keep the video relatively short, but if we solve this out, remember the first thing you've got to do is multiply by the complex conjugate, 30 minus J40 30 minus J 40. And if you do that and work it out, you're going to get that Z sub 2 is equal to minus 3.2 minus J 2.4 ohms. Finally, the last one here, Z3 is equal to ZA times ZB over our sum, ZA plus ZB plus ZC. And let's plug in our parameters. We're going to get Z3 is equal to ZA, which was minus J20, and ZB, which was 20 plus J60 over 30 plus J40. And like before, I'll leave it up to you to do the arithmetic to solve that out. We've done a bunch of examples in previous videos, so feel free to go back and look at those. But when you finish all of that arithmetic, you're going to be left with Z3 is equal to 8 minus J 24 ohms. So now we have all of the pieces that we need. So let's go ahead and draw our circuit again. So I have our voltage source, which is just at 12 at an angle of 0 degrees. Come all the way up here. We'll have our top half, which is exactly the same as it was before. We've got the resistor connected to the inductor in series. Which is 63.2 ohms and J 2.4 ohms. And then you have the capacitor here on the left-hand side, which is at minus J4. But now we've added our new topology. So our Z1, we scroll up here, was 12 plus J4. So what we'll do is, as kind of a shorthand, the real component will be a resistor. The complex one, if it's positive, will be an inductor. And the complex one, if it's negative, will be a capacitor. So if we want to draw this properly, it'll be like this. A resistor to an inductor, and that's 12 and J4 ohms. And then Z2 was minus 3.2 minus J 2.4, so we'll have here a resistor connected to a capacitor, and that'd be minus 3.2 ohms minus J 2.4 ohms. And then down here connected in series, we'll have Z3, which was 8 minus J24, so it would be a resistor that was 8 ohms connected to a capacitor that is minus J 24 ohms. We'll connect the whole thing around. Notice that our transformation also sort of includes transforming what the actual components are. I think that's pretty cool. So what I want to do now is take this circuit, and we're ready to sort of just do our regular series parallel impedances. So I'm going to draw sort of weird version of it. So we essentially have a section, two sections of impedances in parallel now, connected in series with a third section. I gave the game away. That one bottom one I'll call Z3, call it Z1, call that Z2. So Z1 is just these guys in series, so minus J4 plus 12 plus J4 ohms. So that's going to give us just 12 ohms. Z2 is going to give us, what, 63.2 ohms plus J 2.4 ohms minus 3.2 ohms minus J 2.4 ohms. And again, the complex or the imaginary components will cancel each other out. We'll be left with just 60 ohms. And Z3, we don't have to really mess with it at all. That's just still our Z3 there, 8 ohms plus, not plus, minus J 24 ohms. So the next thing we need to do is connect or find our equivalent impedance for Z1 and Z2 in parallel. So we'll call this one Z1, Z2. Now we haven't talked about this particular formula in this class, but we're going to use the two impedance parallel equation, which is the product over the sum. So we're going to say that that's 12 times 60 over 12 plus 60, which gets us just 10 ohms. And so now finally everything connected in series, we're ready to say that ZEQ, our equivalent impedance, is just going to be 10 ohms plus 8 minus J 24 ohms, which means our equivalent impedance after all of that mess is just what? 18 minus J 24 ohms. So now we've got a circuit that's just the source, which is 12 at an angle of 0, connected to an impedance. Ooh, now I could just draw it as a box, but remember, if I was doing it correctly, I would say it's a resistor connected to a capacitor. And that's 18 ohms and minus J 24 ohms. Remember, I'm trying to find our current. We use our regular Ohm's law, V equals IR, which means that I is equal to V over R, which means that in this case, I is equal to 12 at 0 degrees over 18 minus J 24 ohms. Now we've got the bottom portion here, the denominator here is given in rectangular form. This top one is given here in polar form, so we'll need to change one of them. We'll always change from polar to rectangular. Although since it's at 0 degrees, it's pretty easy. The rectangular form is just 12 over 18 minus J 24. And we need to simplify that, again, by multiplying by the complex conjugate, 8 plus J 24 over 18 plus J 24. And like before, I'll leave it up to you to finish this arithmetic. But when you're all done, you'll get that I is equal to 0.24 plus J times 0.32 amps. Or if we wanted to put that back as a polar form phasor, we would just say that I is equal to the square root of 0.24 squared plus 0.32 squared at an angle of the inverse tangent of 0.32 over 0.24. Those are both positive, so we can sort of leave them alone and take the answer as is. So our phasor, our polar form, is just going to be I equal to 0.4 at an angle of 53 degrees amps. And there we go. That is how we use our delta-to-Y transformation to sort of put our circuit in a place where we can just crunch it back down to its equivalent and find that current that we're looking for. So there we go. So there we go. That's all there is to it for the delta-to-Y transformation. As you can see, like a lot of things in this section of the class, everything is quite simple, but it does take a little bit of time to get through. Some of the problems are a bit tedious to solve because it simply just takes time to write everything out. In the next lecture, we're going to kind of put this to the reason that we sort of explored these circuit analysis topics. We're going to talk about our Thevenin and Norton equivalent circuits. which are really important for more complex circuit analysis. That's what's coming up in the next video. So as always, if you have any questions, comments, or concerns, please let me know. If not, I look forward to seeing you guys in the next lesson. Thank you.